Welcome to this video where we are going to look at calculations in the next topic, which is sound. Sound is one of the topics in Form 2 syllabus. So before we go deeper into problem solving in this topic, let's just have a look at some of the major concepts in the same topic. The first one that I want you to bear in mind, or that is automatic as we go through the whole topic, is that sound is a form of energy which is transmitted in space from one point to another. Therefore, it is a wave. A wave. It can travel through solids, liquids, and gases. The speed of sound depends on the type of media through which it travels. Okay? Sound does not travel through vacuum because it is a mechanical wave. That is, it requires a material medium for it to be propagated, because sound is produced when objects vibrate, and these vibrations are transmitted from one particle of the medium into the next particle. So if there is no medium, there are no particles to carry this energy. Now, sound is transmitted through these media in a series of compressions and rarefactions. Compressions are high pressure regions when we are talking about sound traveling through air, and the rarefactions are low pressure regions. A high pressure region will be a region whereby the particles are very close. A rarefaction will be a region where the particles are spaced out more. What other points do we need to consider when we are looking at this particular topic? The first one is the speed of an object, and therefore the speed of a sound. Speed is the rate at which an object covers a particular distance. Okay? And therefore, speed of sound will be the distance covered by the sound divided by the time taken to cover that distance. So speed is a ratio of the distance covered to the time taken. In symbols, we are going to be using V to represent it as the speed, as the symbol for speed, D as the distance covered, and T as the time taken. It follows from this equation that the SI unit of speed is meter per second. Meter per second. Speed of sound in air is about 330 meters per second. So generally, although there are factors which affect the speed of sound in air, and you can go to your course book and those factors are listed, it is about 1,500 meters per second in liquids. For instance, in water, 1,500 meters per second, so it is a bit higher, and about 5,000 to 7,000 meters per second in concrete or solids. So we can see here that the speed of sound depends on the medium through which it travels, and this is a fact for any wave. The speed of a wave depends on the medium through which it travels. As a wave, sound observes the equation. The speed of sound is equals to wavelength of sound times the frequency of the object which is vibrating. Therefore, in symbols, V will be equal to lambda times F. Lambda is a symbol that we use for wavelength, F is a symbol for frequency, and V, of course, is a symbol for speed. And with that, I think we can move to the first question, which is, in this video, I want to go through the examples which are given in the course book. I want to explain each one of them. And remember, we are looking at calculations in sound. So I look at those questions where there are calculations, right? So in example 1 in your course book, you're given that a disc siren with 100 holes is rotated at a constant speed, making 0.20 revolutions per second. If air is blown towards the holes, calculate the frequency of the sound produced and the wavelength of the sound produced if the velocity of the sound in air is 340 meters per second. At this particular point, let's look at a PowerPoint slide where I explain what happens when a disc with the holes is rotating and air is blown through the holes. So here we've got that particular question. So these are the holes and this disc is rotating. It is rotating, and you can see at one point there is a hole which comes in alignment with this spurt of air. So when that jet of air is interrupted, there will be a sound. It's like when you get a test tube and you blow air across the mouth of the test tube, you find that it produces a certain sound. So this is the exact thing. This jet here, there is a jet of air which is blowing here, and then there are holes through which that jet can pass through. So when the hole is in alignment with the jet, the air passes through. But when there is no hole, then that air is interrupted. So it produces a certain sound. And then when it is interrupted, it produces a sound. And then it remains with no sound until the next hole comes in alignment, and the process is repeated over and over again. So you'll find that the rate at which the air is interrupted is going to form the frequency of that particular sound. When you look at these two discs, the first disc is rotating at a lower speed, and the second one is rotating at a higher speed. So the second one is going to produce sound. Those interruptions are going to be more frequent per unit time than the first one. More interruptions of the sound. So the second one is going to have a higher frequency than the first one. So remember, the frequency is the repetition, is the rate at which a particular event is repeated. That is the frequency. So here we're talking about frequency of sound. This one will have a higher frequency than this one. So in this disc, there are n number of holes. There are several holes. And that means, let me just pause the simulation. Over here, there are several holes. There are several holes. So, and the disc is making n revolutions per second. So how do we calculate the frequency of the sound which is produced? We've seen that the higher the revolutions, the higher the frequency. The higher the revolutions per unit time, the higher the frequency of the sound which is produced. So in one revolution, n, for example, here we have it making 0.2 revolutions per second. Let's assume that it makes 1 revolution per second. 1 revolution per second. 1 revolution per second. So the number of holes which are going to interrupt that particular sound will be, let's start counting from here. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. There will be 16 interruptions per second if that disc is making 1 revolution per second. So we are going to have 16 interruptions of the sound per second. In other words, you're going to have 16 happenings, 16 revolutions per second. That means the frequency of that sound will be 16 Hz. If we are told that the frequency of a wave is 5 Hz, it means that there are 5 repetitions in 1 second. That is what it means. 5 repetitions in 1 second. If we are given that it is 10 Hz, it is 10 repetitions in 1 second. If it is 100 Hz, it is 100 repetitions in 1 second. So when we look at repetitions of a certain occurrence in 1 second, we are talking about frequency. Here I've just given you that it is making 1 revolutions per second. Therefore, it means that there are going to be 16 repetitions per second. Why 16? Because there are 16 holes in that disc. So in 1 second, there are going to be 16 interruptions in 1 second. All right, that means that the frequency of the sound that is going to be produced will be 16 Hz. If we increase the speed of rotation so that the speed of rotation is now 2 revolutions per second, 2 revolutions per second, then it's going to make 16 times 2 holes are going to interrupt that spurt of air, that jet of air. It will be 16 times 2. That will be 32 interruptions per second, because the disk is making 2 revolutions per second, and each revolution has 16 interruptions. Okay, so how am I getting this frequency? Number one, I'm getting the number of holes in the disk, which is 16, and then I'm multiplying it by the number of revolutions. So if the number of revolutions is 1 revolutions per second, then the frequency is going to be equal to the number of holes times the number of revolutions, which is 16 times 1, and that will be the frequency, 16 Hz. If it is making 2 revolutions per second, 2 revolutions per second, then I'm going to get the number of holes times how many revolutions it is making per second. Okay, so as a general equation, when you're given a question like this, it's just to get the number of holes in the disk multiplied by the number of revolutions per second, or the number of repetitions per second. So over here, the frequency will be 0.2 revolutions per second times how many holes it has, which is 100 holes, right? So let's go back to the other slide, whereby I will take you through now the calculations for the other questions. So like we have already agreed, this is how we go about calculating the frequency. The frequency will be the number of holes times the number of revolutions per second. So if you're given the number of revolutions per minute, you should be able to convert that separately into number of revolutions per second. So remember, number of revolutions per second times how many holes it has will give you the frequency, and that is how you get 20 Hz. However, in part B, the wavelength of the sound produced if the velocity of sound is 340 meters per second. So we already have the frequency, and we know the speed. We have the frequency of 20 Hz, and the speed is 340. So by using the equation, which is V is equals to F lambda, remember we agreed that sound, being a wave, obeys or follows the wave equation. It must obey the wave equation, which is speed is equals to frequency times wavelength. If we make speed is equals to frequency times wavelength, this is like saying, if I divide we can just draw this triangle here. We can have frequency there, wavelength, put this in some form of a circle, so that when we want the speed, we just cover the speed with your hand, so that below there you can see that it is frequency times wavelength. If we want the frequency, we cover the frequency with our hand like that, and frequency will be equal to speed times wavelength. And if we want wavelength, we are going to say that it is speed times over the frequency. Very, very easy. So you can use this if you have a problem in making a letter to be the subject of the equal sign. So when we substitute 340 divided by 20, we get 17 meters. That will be the wavelength of the sound. Let's look at the next question. The next question is similar to what we have here. This is about a cogged wheel. A cogged wheel with a stiff card just next to the cogs. You'll find that when the wheels rotate, it's going to sort of like, for example, produce a sound, because it's going to vibrate. The paper is going to vibrate. And remember, sound is produced when objects vibrate. In fact, one of the examples we use in the lab to demonstrate that sound is produced when objects vibrate is you can get a meter rule, clamp one end and then you allow the other end to vibrate, it's going to produce sound. Look at a drum that we use in music. When the skin of the drum is vibrating, it's going to produce sound. How about the wire of a guitar? When the wire vibrates, it produces sound. So sound is produced when objects vibrate. Even when I'm speaking to you, my vocal cords are vibrating and they are producing sound, which is being captured by the microphone and then converted into other forms of energy. That is a subject for another topic. So this cogged wheel will make this paper to vibrate. Okay? And just like previously, you can see that, we are given that a cogged wheel rotates uniformly, produces sound of wavelength 1.65 meters. If it makes 10 revolutions per second, find the number of teeth on the wheel, given that the velocity of sound is 330 meters per second. Again, here we are going to use the fact that frequency of the sound which is produced here is going to be given by number of teeth times the revolutions per second, or rotations per second. That is how we can get the frequency. And then we are going to remember that speed is going to be equal to frequency times wavelength. When you combine these two, because this frequency can be replaced by speed, that frequency can be replaced by speed. Let me just write it here. That frequency can be replaced by speed over the wavelength. It can be done like that. We've got the number of teeth, and we can get the number of revolutions per second. And you can see that the speed of sound is given over there. So very quickly, this is how the calculations are done. Frequency is number of teeth times the revolutions per second. And frequency is lambda, V over lambda, which is 330 over 1.65, which is 200 Hertz. Now we can use that 200 Hertz. We substitute it here. That 200, we substitute it here. Now this is a substitution into the first equation. It's going to be equal to number of teeth times revolutions per second, which is given there. And we find that the number of teeth will be 20. It's just as simple as that. Let's go to the next question. This question is about one of the methods that we can use to determine the speed of sound. And it's called the clap and echo method. How does the clap and echo method work? This is how it works. This could be a huge wall, maybe of a building like the school hall or something, and then you position yourself here, maybe at a certain comfortable distance, like maybe 100 meters or something like that. This will be the distance, and then you're going to produce some sound. Maybe you can get two pieces of wood and clap them together. That's why the method is called clap and echo method. When that sound travels, it will be reflected by nearby buildings, the trees, buildings, and any other large object is going to reflect the sound. And that sound will come back to you, and then you will hear the reflected sound. The reflected sound is called the echo. So let's assume that the sound has been produced here. So it travels towards the wall. It travels like that. It will move and hit the wall, and then it will be reflected. When it comes back to you, you will hear the reflected sound. You will hear the echo. However, the distance that the sound has traveled will be d plus another d. So if you are to work out the speed of this wave, you will say that it is d plus d divided by the time it takes between clapping and hearing the echo, because that is what the second buoy does. The second buoy starts a stopwatch and stops it when he hears the echo. So it's like he's taken this time here, this time for distance to travel through d plus d. Okay, and that is exactly what we are going to do in the solution. So in the solution, I've already shown you that this distance here is 200 meters. The time it takes for sound to move from that point, hit the wall and come back is 1.2 seconds, and therefore speed is equals to distance over time. The distance is d plus another d. We usually refer to that as 2d over t. You have to read the question carefully to find that have you been given the t and what does the t represent. All right. So 2 times 200 divided by 1.2, you get 333.3 recurring, and that is the approximate speed of sound in air. You find that in some questions they are giving you 340 meters per second. Some questions they can give you 320 meters per second. In others they can give you 330 meters per second. It really depends on the other factors which affect the speed of sound in air, such as temperature, such as humidity, because these are the factors which affect the speed of sound in air. But it ranges around that value, 320 all the way to 340 meters per second. Let's go to the next question. The speed of sound in air is 3 meters per second. A loudspeaker placed between the two walls. Okay, there is a wall here, and there is another wall here, right? And there is a loudspeaker between the two walls. Let's say this is wall A, this is wall B. Okay, and then there is a speaker in between them, but nearer to wall A. So the speaker will be somewhere around here. This is where the speaker will be. It's nearer there. Is sending out constant sound pulses. How far is the speaker from wall B? So we are going to say this is what we are looking for. This is what we are looking for. How far is the speaker from wall B if it is 200 meters from wall A? This is 200 meters. It's 200 meters. And the time between the two echoes received is 0.176 seconds. So there are two echoes. Why two echoes? When sound is produced here, sound travels in all directions. So there will be sound traveling in this direction. There will also be sound traveling in this other direction. When travels in this direction, hits the wall and then comes back, we can record the time it takes to receive the first echo. And then simultaneously, sound was traveling in this other direction, hits the wall, gets reflected, and comes back. And we record the second time, which is T2. These two times are going to be different because the distances are not the same. So it takes a shorter time for that wave to cover this short distance, and here it takes a longer time. Now it is the difference between the two T's that is given. Look at the question. The time between the two echoes received is 0.176 seconds. So how do we calculate this distance here? First of all, we can use the equation V is equals to 2d over t to calculate t1, because we know the speed, we know the d, and we know we can get the t because t is the one which is unknown. Look at the question. We have the speed and we have the distance 200 meters, so it's clear we can get t1 because we are going to say this will be 340, this one will be 2 times 200 divided by t1, and we can get t1. We can repeat the same for the second echo and get t2. Now when we do that for the second echo, we are going to say the speed is 340. The distance here will be, by the way, this d is a general d. In fact, I should have used a different symbol altogether so that I don't confuse you by using these symbols. So I think this one here, I want to change that D to be something else so that the symbols do not conflict. So I'm going to say this one is D. This one is D. Let me say this is D. Capital D. Well, the small d is what we are looking for. So when we are on the second part, 340 meters per second is the speed. 2 times D. Now this D is this D. Remember, it is unknown. And then the T2 is here. So you can go ahead and calculate the T2. Remember, here we got T1. It has a value. Here we get the T2. It will not directly have an exact value because D is still unknown. But we've been told that the difference between the two times, T2 minus T1, because T2 is higher than T1, is this value here. Now, where is it? It is this value. And by forming that equation, we can be able to calculate the unknown, which is D. Again, I've already worked out this equation, and this is how it is worked out. If, for example, you are doing these questions and want to follow from point to point, always pause the video, look at what I've written down there, and you will just be fine. But remember, diagrams are very important. A diagram like this one will help you to be able to understand what is happening. The use of an equation until we get the first value of T1 there. The use of this equation until we get the second value of T2 here. And then we say T2 minus T1 is this value. I found it appropriate to use x of 170 because this one will be, when I divide here, I cancel this when I get 170. I find it better to use x over 170. And by the way, the unknown, I called it x in this calculation. It really does not matter, okay? What symbol you use. Just use a reasonable symbol. So that is what I would use for T2 as x over 170. How about T1? T1 would have been, the moment I saw this one was out of 170, I realized I could also get a 200 over 170 here. So I just need to divide here by 2, I get 200, and here divide by 2, I get 170. So instead of using 1.176 seconds, which is a rounded up value, I would use an exact value, which is 200 over 170 is equals to this value. It makes our value to be more accurate because it doesn't have rounded up values, although this one definitely has rounded up values, but it's a value that we've been given in the question, so we don't have to worry about that. But wherever you are carrying out a calculation, remember to use as exact values as possible where possible. If it's possible, then round them up. And this is just a mathematical manipulation, in which case you can use a calculator to confirm that the value of x is 229.92 meters. Let's go to the next question, which is the last example here of the application of the equation 2d over t. This equation 2d over t is used in so many situations. It can be used to find the depth of the sea, by transmitting sound through the water. There will be a transmitter and then there will be a receiver. Here we've put them at different positions, but when it comes to the actual situation, we may find that the transmitter is the receiver, is the same as the receiver, as we do in ultrasound. When we go for ultrasound, a diagnosis, you find that ultrasounds are produced, they travel into the body, they will hit the organ, and then that organ is going to reflect the sound. So it travels through a distance d, through another distance d, and that object records the time. We are able to tell so many things about how far is that organ from the skin. It can calculate that, plus so many other things. So objects, applications such as the use of ultrasound in medical diagnosis, they use this simple equation. V is equals to 2D over T. When it comes to determining the speed at which an object is moving, maybe a car is moving, the police would use something referred to as a speed gun. The speed gun is directed towards the oncoming vehicle. So it produces microwaves which are going to hit the bodywork of the car, and then the bodywork of the car is going to reflect the sound. So the transmitter is the same as the receiver, and once it does that, it's going to give us so many physical quantities. It can tell us how fast the car is traveling. It can tell us how far the car is from the speed gun, that is from the traffic police, and so many other things can be calculated. But in that situation, we are bringing in something else, which is we are bringing another concept which is beyond the topic. But basically, the equation 2D over T is used even in that particular situation. So it is used in so many other applications in real life. Here it appears to be so simple, and we might think that it's not as relevant as, because it appears to be very simple, but in real life, it has a lot of applications. So let us look at this equation 2D over T to determine how deep this ocean is. So we are going to call the depth of the ocean to be D, and then the time taken, I think the time taken is given as 10 seconds. Let's read the question. The ship shown in that figure sends out an ultrasound whose echo is received after 10 seconds. So this will be our value of T. Let me change the color to be blue. This one will be the value of T. If the wavelength of the ultrasound in water is found to be this much, this will be the wavelength. And the frequency of the transmitter, that is the frequency of the vibrating object, is 50 kilohertz. 1 kilohertz is same as 1,000 hertz. So this one will be 50,000 hertz. Okay. Calculate the depth of the ocean. Calculate D. So it's just like being asked to calculate the distance between the two walls, or calculate the distance from where the boy was clapping all the way to the wall. A very simple concept. So again, here I've given you the calculation, and by using V is equals to 2D over T, and we remember that V is equals to lambda F, therefore lambda F is equals to 2D over T. Lambda is 0.05 meters, while the frequency is 50,000 hertz, is going to 2D over 10. We find that the D is given as 125,000, and that will be 125 kilometers. This, according to that question, this appears to be like a very deep part of the sea, or a very deep part of the ocean, all right? But that is not the point. When we think about physical quantities in physics, there is a section of physics which requires us to estimate the magnitude of physical quantities. That is, when you look at an object, if you look at an elephant, for example, you are able to say this elephant could be so many tons or so many thousands of kilograms. It is between this value and this value. And then when you look at a small object such as maybe a bird, you can be able to estimate that this bird is so many kilograms. It's not common for you to say the mass of this particular bird, which is just flying in the forest, from one tree to another, and then you say that it is 100 kilograms. Such a bird will be a very heavy bird. Or if you say the depth of this ocean is 125 kilometers, if you know the length of 1 kilometer, then you are able to say this must be a very deep part of the ocean, 125 kilometers. Okay, so you are able to question the the calculation, which is all right because you're comparing it with something which you know. This is called estimation of the magnitudes of physical quantities, which we deal with in physics because it helps us to make some judgment or to even criticize a value. For example, it will be all right if you go ahead and criticize this value and say this value, this depth cannot be real. It is just too deep. Now, when we come to the values given, maybe the mistake was made somewhere around here. Maybe the frequency is not 50 kilohertz. It could be 5 kilohertz. That will have reduced this value to 12.5 kilometers. Now that will be reasonable. Or maybe a mistake was made in the timing. However, sometimes when values are given in the textbook, they are just given to test whether you can be able to carry out certain calculations without bothering whether that value makes sense or not. Just to be able to use the equations which are given. And that brings us to the end of this particular lesson, where we are looking at examples which are given in the topic sound, and we are looking at calculations. I'd like you to go now to your course book. Let me just open the course book. So I'd like you to go to the revision exercise and look at the questions which require you to calculate or which involve calculations. Like, for example, question 2b, you can start from A. You can go to question 3. It is also on calculation. And remember, if you don't have the course book, you can always pause the video and copy the question in your notebook. Question 4, A and B. Let's look at the next question. Question 7. Question 8. Question 9. Question 11. Question 12. Question 13 and question 14. You can use those questions to practice. Remember, in the next video, in calculations in sound, I look at the solution to this question. And remember, it is always good to try them out, because if you're learning this topic for the first time, or if you are revising, the best revision comes about when you really engage with questions, when you practice answering questions. Now, why am I looking at calculations? I'm doing that because it has been shown that most of the questions which give students challenges, they are those questions which involve calculations. So go right ahead, give me the answers to this question, and I'll see you in the next video where we discuss each one of those questions. Bye-bye.